Hello, Physics 30s. In today's lesson, we are going to continue our discussion of spherical mirrors, although this time around we're going to approach it from more of a mathematical perspective as opposed to the qualitative perspective that we dealt with in the last lesson. Learning outcome for today is to describe quantitatively, this time, simple optical systems consisting of only one component for both lenses and curved mirrors. Okay, so I have a picture on the bottom of the screen of a concave mirror. So I'll just label this as concave. Concave because light rays are striking the inside of the sphere. What I'm going to do is I'm going to introduce a bunch of variables that can be used to describe different things about the object and the image. Then after we have a proper understanding of these variables, we can start to play around with some mathematical equations that relate these variables. First variable is r. R is the radius of curvature. The radius of curvature would be the distance from the vertex of the mirror. So we could label this as V, the vertex. This as the focal point F. And this as the center of curvature C. The radius of curvature would be the distance from the vertex to the center of curvature. F is what we call the focal length. And the focal length, as you can see in the diagram, it's that red arrow. It's the distance from the vertex of the mirror to the focal point. DO represents the distance from the vertex of the mirror to where the object is located. So on this diagram, my object is a candle. So I could represent it with an arrow that's just pointing straight up. Then you have your image that's inverted or upside down. And then to just show the object distance. So again, the object distance would be the distance from the vertex to the location of the object. We call that DO. DI would be the distance from the vertex of the mirror to the location of the image. When we talk about these distance values, they're horizontal distance. HO would represent the height of the object starting from the principal axis or relative to the principal axis. So this vertical height here would be HO. HI would be the height of the image starting from the principal axis. In this case, we'd go downward, and then we have HI. Okay, now, just before I move forward, I want to quickly summarize some of the results from the spherical mirrors hand-in assignments in terms of like information you should know about the mirrors. So basically on the assignment, I had you deal with every possible scenario of where an object is placed. So in one scenario, you had the object where it was outside the center of curvature, on the center of curvature, between the focal point and the center of curvature, on the focal point, or within the focal point, between the focal point and the vertex. So let's look at what some of those results are in terms of like what you should have observed by completing the assignment. Okay, first things first, if you're dealing with a convex mirror, it doesn't matter where you put the object. For a convex mirror, regardless of where you put the object, you are always going to get an image that is virtual. Erect. And reduced in size. The example I used for that from the last lesson was the surveillance mirrors that are used in convenience stores. Now, for a concave mirror, it's a little bit different. Okay, let's say you had your object outside of the center of curvature. So we could say this. We could say the distance of the object is beyond the center of curvature. In that situation, you should get an image that is real, inverted, and is reduced in size. If we take the object and then we put it directly on the center of curvature, so I could say DO is equal to C. Your image will again be real. The orientation should be inverted. And this is kind of a tough result to get, but technically speaking, if it is directly on the center of curvature, the size of the object and image should be the same. However, I suspect when you did it, you probably ended up getting a reduced image. Well, that's probably not it's probably not your fault that that happened. It's more so just using Microsoft Word art to construct the mirrors, and just when you construct the rays, just things not occurring as they should. But technically speaking, it should be the same size as the object when you put in terms of the image when you put it on the center of curvature. Okay, let's then put the object here. Well, as you can see in the picture. So in this one, we're between the center of curvature and the focal point. So I could say that the location of my object is less than the center of curvature, but bigger than that focal point. And in this case, you should get it's real. And then you can see in the picture here, real, inverted, and it becomes enlarged. This shouldn't be surprising. As you bring an object closer and closer to the mirror, I would expect the image that I formed to get bigger and bigger and bigger. I think that happens with the convex mirror too. Like as you bring the object closer and closer to the mirror, it does get bigger and bigger, but I think no matter what, it still ends up being reduced in size in comparison to what the object is on a convex mirror. Okay, now let's go to the focal point. This is the tricky one. So let's do blue here. So we're directly on the focal point. So we could say that DO is equal to F. If you do this one correctly, when you construct your rays, you should get rays that are parallel to each other. If rays are parallel to each other, they can never intersect. Even if you backwards extend the rays through the virtual side of the mirror, they cannot intersect. If the rays do not intersect, then that means that there is no image. So if the object is right on top of the focal point, you don't get an image. Now the last one, this is also a tricky one. So let's do orange here. Let's put the object somewhere between the vertex. So I'll say V and the focal point. So DO would be less than the focal point, but bigger than the vertex. When you do this one, if you construct the rays correctly, the rays will not intersect on the real side. However, if you backwards extend them through the mirror, you should get an intersection point behind the mirror. If you get an intersection point behind the mirror, this tells me the image is virtual. The orientation is erect. And because you're quite a bit closer to the mirror, the image should be enlarged in size. Now, just one other thing, just kind of like a relationship between the relationship between the type of the image and the orientation. You should have noticed that when you did this, anytime that you have a virtual image, you must get an orientation that is erect. And anytime you get a real image, you must get an image that is inverted. This must always be the case. All virtual images will be erect, all real images will be inverted. It's not possible for you to have a virtual image that's inverted or a real image that is erect. And we'll talk more about this later when we get into some of the equations. Okay, so that's a little bit of a summary of everything you should have observed from the spherical mirrors hand-in assignment. Now, let's continue going through these variables, and now we're going to talk about the sign convention on the variables. When I say sign convention, it means that these variables can sometimes be positive or negative. It just depends on what the type of the image is and its orientation. First of all, the focal length, we're going to put a positive in front of the value if we're dealing with a concave mirror or a converging mirror. The reason being is that for a concave mirror, you have a real focal point. We're going to associate the real side of the mirror as being positive. And if you have a convex mirror, well, everything's flipped around. Your center of curvature and your focal point are now on the virtual side. So that would be a virtual focal point. And if you have a virtual focal point, we're going to represent virtual as being negative. The object distance, the distance from the vertex to the object, is always going to be positive because your object, well, it's real. The image distance is positive if the image is real. So again, that's staying consistent with the notation I introduced for the focal length. And it's negative when we're dealing with a virtual image. The object height, typically we always draw the arrow for the object height pointing up. So we're always going to assume it's in an erect orientation. The image height, well, that can be positive or negative. If the image is erect, we're going to put a positive sign in front of HI. If the image is inverted, then we put a negative sign in front of HI. So long story short, if something's real, positive. If something's virtual, negative. In terms of height, if something is erect, we put a positive sign in front of it. If something is inverted, we put a negative sign in front of it. Before we get into the equations, there's just one other physical quantity that I want to introduce, and that quantity is called magnification. Magnification is a ratio of the size of the image to the size of the object. So in a sense, what magnification tells you is it tells you how much bigger is the image in comparison to the object. Now, there are two ways you can calculate this. To calculate the magnitude of magnification, yes, magnification can be a positive or a negative number, but I don't want to worry about that right now. And I don't want to provide any interpretation as to what positive or negative means. We're just going to deal with magnitude strictly when we go through the problems and how I like to approach it. Okay, there's two ways to calculate magnification. So again, it's a ratio of your image size to your object size. So that could be a ratio of the distance from the vertex of the mirror to the image to the distance from the vertex and mirror to the object. So the ratio of di over do. That is also equal to the ratio of the image height to the object height. I'm not going to show this, but you can get that relationship by applying a geometry rule dealing with similar triangles. But all we need to worry about right now is the magnitude over a magnification is di over do or hi over ho. We're just going to take the magnitude only. So if we look at this picture right here, if I was to make a rough guess as to like what the magnification might be, well, here's my object height. Here's my image height. I don't know, maybe the image height is 2 times the object height. It looks like it's gotten bigger. So I'd say the magnification is somewhere around 2. Probably between like 1.5 and 2 if we actually pulled out a ruler and measured this to scale. Okay, now we have a series of equations we can use to relate all these different variables. The first one tells us that to calculate the focal length is just the radius of curvature divided by 2. Well, that's how we define the position of the focal point. We said it was the midpoint between the vertex and the center of curvature. Therefore, the radius of curvature cut in half is the focal point. On your formula sheet, you're going to see an equation, I believe it's in the wave section, that says 1 over f is equal to 1 over di plus 1 over do. I'm not going to derive the equation. We're simply going to assume it is correct, and we're going to utilize it. So 1 over the focal length is 1 over the image distance plus 1 over the object distance. Again, I've numbered it because it is on the formula sheet. We also have this one. We have magnification is equal to the image height over the object height is equal to negative. It's kind of weird why that negative's there. Di over do. So that's an equation that basically allows you to calculate the magnification. Just notice this, it's the exact same equation that up at the top right here, except I just took the magnitude. If you take the magnitude of the magnification, then it gets rid of this negative sign. So the question really is, well, why is this negative sign here? What's the point of this? Okay, it's all about relating just these 4 variables together. So let's not worry about the magnification part. Let's just worry about relating hi, ho, di, and do. And what I'm going to do is I'm going to do a quick manipulation of this equation, and I'm just going to manipulate the equation for hi. To get hi by itself, you just bring ho to the top, and then you'd have hi is equal to negative di ho divided by do. Now, in terms of why that negative sign exists, it's basically like a correction factor. So what it does is it's going to ensure mathematically that if you have an object that is real, you must get an inverted orientation. So let's go through this. So think about this here. Let's say you have a real image. If you have a real image, that means that your di value would be positive. Okay, it's greater than 0. So if we plug all the numbers into the equation here, so if we had di is positive, ho is positive, and do is positive, and you multiply by that negative, that would give you a negative h value, which is inverted. Therefore, what it's doing is it's forcing you to get the inverted orientation if you're dealing with a real image. Now, the opposite is going to be true. If you have a virtual image, so a virtual image, according to our sign convention, tells me that di is a negative number, so that's going to be less than 0. Well, let's see what happens with the math if you play this out. If di is negative and you multiply by that negative, it gets negative times a negative is a positive. ho and do are always positives, therefore you get a positive hi value, which means if you have a negative di value, which is a virtual image, you must get an erect image. So really, that's the only reason why that negative sign exists in the equation. It just ensures that you're always going to get, if you have a real image, you'll always get an inverted orientation. If you have a virtual image, you're always going to get an erect image. It really has nothing to do with calculating the magnification. That's why when I calculate the magnification, I'm just going to take the magnitude of everything to do it. All right, let's go through 3 examples. We're going to utilize these equations. Okay, so I have a 5 centimeter tall object. So that is the height of the object. So I'm going to call that HO. And your height's always positive of the object. It's placed 60 centimeters away from a convex mirror. So that's the distance of the object. And again, the distance of the object is always positive because your object is a real thing. It tells me I have a convex or a diverging mirror that has a radius of curvature of 80 centimeters. Now, the radius of curvature is going to be negative. That's because the center of curvature is on the virtual side of the mirror. And we're dealing with a convex mirror. Again, a convex mirror has a virtual focal point and a virtual center of curvature. Well, my equations don't have radius of curvature in it, so let's just quickly calculate what the focal length would be. So the focal length would just be the radius of curvature divided by 2, which would be negative 80 centimeters over 2. Therefore, my focal length is going to be negative 40 centimeters. Okay, now it says describe the image formed. To provide a proper description of an image, what I want to know is the type of the image. Now, to figure out the type of the image, I can know whether it's a real or a virtual image if I just know what the sign on DI is. So I want to calculate DI. I also want to know the orientation. What variable is going to tell me my orientation? Well, the image height. Because if it's positive, it's going to be erect, and if it's negative, it's going to be inverted. And then the other thing you want to know is like what's the size of the object image in comparison to the object. Okay, so you want to calculate DI HI. Although if you're clever, like you should recognize that convex mirrors always give you virtual images that are erect and reduced. So I suppose qualitatively speaking, you could just identify that immediately if you recognize the pattern for where you put an object on a convex mirror. But I want to go through the actual math to show you that I can prove that I'm going to get a virtual erect and a reduced image. All right, let's start off with the equation. 1 over f is equal to 1 over di plus 1 over do. I want to solve for di because it's going to tell me the type of image. So let's subtract 1 over do from both sides. So I'd have 1 over di is equal to 1 over f minus 1 over do. Now, I'm not going to isolate for di. I could do it. It's just going to involve some annoying math that I don't want to deal with. The way I'm going to solve for di is I'm going to calculate 1 over di and then just invert that number to calculate the correct value of di. Okay, so I'll just solve for 1 over di and then just invert it after we have that value. Okay, let's plug numbers in. So we have 1 over a negative focal length, negative 40 centimeters. Subtract 1 over do, which is positive 60 centimeters. And if I do this, I should get a negative number at negative 0.0416, and it's a repeating decimal number. And because we're finding inverse 1 over di, that would actually be inverse centimeters. Well, to figure out what di is, now we just need to invert this number. So let's go 1 divided by that number to calculate the correct value of di. And when you do that, you should get a really nice whole number. So di would then be equal to negative 24 centimeters. And I could provide a quick justification here. I could say image is virtual since di is a number that is less than 0. Let's calculate the hi value now. So now I'm going to use that other equation. We're not going to worry about the magnification part of it. It's not really helpful in doing that using that equation. So what we have is hi over ho is equal to negative di over do. Let's get hi by itself. So to have hi is equal to negative di ho all divided by do. Plug the numbers in. Okay, DI is negative 24 centimeters, multiplied by HO, which is positive 5.0 centimeters. Divide this by DO, which is positive 60 centimeters. And then we get an HI value. And again, you can see here the point of this negative correction factor. It's going to turn the negative to a positive, so I'm going to get an erect image. Okay, so I'm going to get a number that is positive 2.0 centimeters. Box side, we can provide a quick justification. And we could say image is erect. Since HI is positive. The last thing to do is just talk about the image size. So to talk about the size, we need just to compare the height of the object to the height of the image. So let's take the magnitude of the image height, which is 2 centimeters. Let's compare that to the object height. Well, it's smaller. So it's less than the object height, which is 5.0 centimeters. If the image height is less than the object height, we can say the image is reduced in size. Again, it doesn't matter where you put this object in front of a convex mirror, you are always going to get this combination, virtual, erect, and reduced. Although, as I bring the object closer to the mirror, I would expect the size of the object to get a little bit bigger. Second example, I have an object located in front of a concave mirror with a focal length of 40 centimeters. Well, let's write that down immediately. So, focal length. Now, a concave mirror has a real focal point. So a real focal point, we're going to write down a positive in front of it. Now, it tells me it produces an erect image. Now, it is important that, it's very important the question tells me this. If your image is erect, what type of image must it be? Well, all erect images must be virtual. If I have a virtual image, what does that tell me about my DI value in terms of the sign convention? Virtual images have a DI value that is less than 0 because they're on the image is going to form on the virtual side of the mirror. Okay, so that's important. We're going to come back to that momentarily. Okay, it says that the image is 4 times the size of the object. Well, that's the magnification. Okay, so I'm going to start off with an equation for magnification. So let's say magnification. Again, you can write down it's either the ratio of image distance to object distance or height, object height to image height. I'm going to look at the relationship between distance here. So the magnification magnitude would be the magnitude of DI over DO. Okay, I'm going to replace the magnification with 4. I'm going to break this absolute value apart a bit. So I'm going to write down the magnitude of DI over, well, the magnitude of DO, we don't need to write down magnitude because DO is always a positive number. So I guess write down DO. If I manipulate this equation for DI, I would have DI. That's the magnitude of my image distance, would be 4 times DO. Now, here's where I need to use that important piece of information that tells me that the image is erect. Okay, so I just identified if it's an erect image, it's virtual. That means that DI has to be a negative number. So when I drop the magnitude sign, now I need to account for direction. Well, I'm going to write it as negative 4 DO. I'm going to box this, and I'm going to call it equation number 1. Okay, so I made use of this right here. Okay, so when I drop the magnitude sign on the DI, I had to account for what direction DI is. It's going to be a negative number because the image is erect, which means it is virtual. Okay, let's write down our equation. 1 over f is equal to 1 over di plus 1 over do. I'm going to take equation 1 and sub it into this equation. So sub equation 1 in for di. Now, when I do that, I'm going to get 1 over f is equal to 1 over negative 4do plus 1 over do. I'm going to rewrite this as 1 over f is equal to, just take the negative sign and move it up to the numerator. So I'm going to write down negative 1 over 4do plus 1 over do. Okay, I know what the focal length is. I need to calculate do, but in order to calculate it, I need to combine these two fractions. Now, these two fractions currently do not have a common denominator. This would be like equivalent to taking the fraction. If I get rid of the variable, it would be like taking negative 1/4 and then adding 1. Or you could say like 1 over 1. So they don't have a common denominator. So I'm going to write down need common denominator. But look at this one. If I have negative 1 over 4 plus 1 over 1, what's the common denominator between 4 and 1? It's 4. If I have 4do and do, what's the common denominator between 4do and do? Well, it's 4do. So your common denominator CD would be 4do. Okay, let's rewrite the fraction out now with a common denominator. So we'd have 1 over f is equal to negative 1. Well, the first fraction doesn't get affected because it already has the common denominator of 4do. Now, if the second fraction is going to have a common denominator of 4do, what number would have to go in the numerator so that if I worked backwards, I could reduce it to the fraction 1 over do? Well, it'd be 4. 4 over 4 would give you 1 over do. So that is my common, that's my equivalent fraction with that common denominator of 4do. Okay, now, because the denominators are the same, I can add the numerators together. So negative 4 and 1 would give you positive 3 over 4do. I want to solve for do. So to get that by itself, I'm going to bring do up to the top and then also f up to the top. So I believe if I do that, I should get do is equal to 3 over 4 times f. And by the way, this is all my work for part A. Let's plug the numbers in. So this would be 3 over 4 times the focal length. The focal length is positive 40 centimeters. And then if I get a do value, that would be positive 30 centimeters. B is super easy to do because now that we have do, we can just go back and use equation 1. So equation 1 was di is equal to negative 4do. Plug the numbers in. do is positive 30 centimeters. And then I would get di is equal to, well, we're doing two significant digits, so it would be negative 120, but in scientific notation, 1.2 times 10 squared centimeters to two significant digits. Okay, so that one's a bit tougher because you do need to remember how to actually find common denominators between fractions, which I hope you are still capable of doing. 3. Light from a distant planet is instant on a converging mirror located on the Earth. Okay, I'm going to start off by drawing a picture. Okay, so let's say we have our planet. And then way over here, we have a converging mirror, so a concave mirror. So light from the sun hits this planet, reflects off, then let's follow like one ray of light. So one ray of light goes all the way across the vastness of space. It hits this concave mirror, and then it reflects. And it reflects onto a screen. So I'll draw the screen. Okay, now the problem tells me the focal length. So your focal length f, and again, it's a concave mirror. So a concave mirror is going to have a positive focal length. So that'd be f is equal to positive 45.0 centimeters because it's concave. Okay, now I want to identify the other variables. So let's identify di and do. And I'll do this in a different color. So let's use green. Okay, do would be the object is the planet. Okay, so you have the distance from the planet all the way to the vertex of the mirror. We call that do. What the problem wants me to calculate is di, which is the distance from the vertex of the mirror to the screen. So that's di. So what we're doing is we're using a mirror to form an image on a screen of this planet. Now, at first glance, it seems like you do not have enough information to solve this problem, because we're going to use the equation 1 over f equals 1 over di plus 1 over do, but I don't seem to know what do is. But think about this. How does the distance from the planet to the mirror compare to the distance from the screen to the mirror? Well, it's really, 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 really big. In fact, in comparison to the distance from the mirror to the screen, we can say the distance from the mirror to the planet is pretty much infinite. It's a huge number. Okay, now let's go through the math. So we have 1 over f would be equal to 1 over di plus 1 over do. We want to solve for di, so that'd be 1 over di is equal to 1 over f minus 1 over do. Just plug our numbers in. So concave mirror, converging mirror, positive 45.0 centimeters, minus 1 over a huge number. Well, what's 1 divided by a ridiculously large number? 0. Well, pretty much 0 anyways. So we can actually ignore that 1 over do term. So that just tells us now that 1 over the focal length is equal to 1 over positive 45.0 centimeters. Therefore, but we're not calculating the focal length here. We're calculating, let's change that. My bad. We're calculating 1 over do. 1 over di, I mean. Okay. Yeah. So this would be 1 over di is just equal to 1 over 45.0 centimeters positive. Therefore, the distance from the vertex to the screen is just equal to the focal length of the mirror. So a little bit of a trick question. Okay, so that's it for this lesson. We've talked about spherical mirrors both qualitatively and quantitatively, and you can practice this work quantitatively by completing the assignment called Mirror Equations. And in the next lesson, we'll shift gears and start to talk about refraction of light. I'll talk to you then.